Welcome to RF transceiver design course. We are discussing about passive components and impedance matching. Up to now we have discussed starting from the transmission line, and then we have discussed Smith chart, how to do the impedance matching using a Smith chart, using ZY Smith chart, and we are also discussing the various method based on the Q, how to do the impedance matching. So, we will see two more impedance matching circuits. So, one of the widely used circuit, that is a tapped capacitor resonator. So, this resonator is also used as mentioned here in the uh, oscillators. So, this can also be used for impedance matching. This is called a tapped capacitor resonator, where C1 C2 are the tapped and there is a R2 resistance, and at the input side there is input impedance R in, which will be converted to the R2, or R2 can be converted into the R in. So, the relation between R2 R in and the parallel capacitor C1 C2 can be written as R2 by R in, which is equal to 1 by SC2 upon 1 by SC1 plus 1 by SC2 square. So, this can be, there is a direct relation between R2 by R in, the resistance ratio between C1 by C1 plus C2. So, the network transform in this resistance R in downward to a value of R2, and resistance R2 will be upward to the value of R in. So, we can do the means downward means resistance R in, which is high, to the R2 low, and we can also make R2 upward from R2 to the R in. This circuit is widely used in oscillators, resonators, because it is a resonator and impedance matching both is combined, and it mostly in the Colpite kind of oscillator. So, this is used in the oscillator as well, and what it do, it helps to couple energy out of the tank without degrading the quality factor Q. So, this is the basic about tapped capacitor resonator. Now, we will see how to solve this, how to find out the value of inductors and capacitor for the different impedance R in and R 2. So, if we try to convert the parallel RC in series, because there are a RC which is a parallel, if we try to convert parallel RC into series, so the series resistance R2S, this is a here this R2 and C2 are parallel. So, if we try to convert into the series, that R2S, we already have seen this equation, we can convert the parallel to series by using this equation, R2 by Q2 square plus 1 and C2S C2 Q2 square plus 1 by Q2 square, and Q2 is a Q of the parallel RC section, that is R2 into C. This is parallel RC section, which is a Q2 is given by the Q of the parallel RC section. Now, the series resistor may also be viewed as a result of transforming R in. So, RS can be converted. So, RS, which is equal to R in Q square plus 1. So, this equation, that is RS, which is equal to R in by Q square plus 1. So, this is a R in, and if we want to convert to the RS, so the Q is a quality factor of entire this tapped capacitor resonator. So, RS, which is equal to R in by Q square plus 1. Now, if we equate this RS to expression RS, and if we try to solve the Q2, we will get a Q2, because Q2 is a unknown. So, Q2, which is equal to R2 by R in Q square plus 1. So, it is just by equating RS. So, here R2 by Q2 square plus 1 equal to R in Q square plus 1. So, here this will, we can write R2 Q square plus 1 is equal to Q2 square plus 1 by R in. So, Q2 square can be given by R2 by R in Q square plus 1 minus 1, and then the square root, you will get the final expression Q2. Now, based on this value of Q2, you can get the value of C2. So, C2 which is equal to Q2 by omega naught R2. R2 already known, Q2 already known, we can find the C2. Now, just equate the value of Q2 here, we can find the C2. Now, we will try to derive the C1. So, because the two capacitors are in series, we can write C equivalent which is equal to C1 C2S by C1 plus C2S, and the network Q then can be expressed for this Q which is equal to 1 by omega naught R2S into C equivalent. C equivalent we will keep here, we will get the expression of Q. So, your C1 will be written equal to C2 Q2 square plus 1 by Q into Q2 minus Q2 square. So, finally, you will get the value of C1. Here we can replace the Q and C1 C2S value, that is this, we will get the final expression C1 in terms of C2, Q and Q2. So, we can find C2 by using this equation, we can find Q2 by using this equation and Q of the tank circuit, and inductor L is a straightforward, that is L which is equal to R in by omega naught Q. So, we will try to try to see one example that how can we find out all the values. So, if your R in is a 50 ohm, so as I told that we are converting the high impedance to the low impedance. So, R in is a 50 and R2 is a 5, and quality factor, that is a 40 that we required for this tank circuit. So, we can directly find the value of inductor by using this formula R in by omega naught Q. So, that is a 0.199 nano Henry. Next, we find the bottom capacitor C2. So, we know the Q, we know R2, R in omega naught and R2. So, we can get the final value of capacitor, that is a 401 picofarad. Now, we can find other capacitors value also, that is 186 picofarad. So, this in this example, one thing that is important to understand, that the value of inductor is very less, and on chip oscillators or on chip circuits, we can reduce the size of the circuit by using this technique, that is a tapped capacitor resonator technique. Another technique, that is a tapped inductor capacitor, where in Hartley oscillator this is widely used. So, in that this is inductors are tapped. So, there are two inductors and one capacitor, and it is R2 which is resistance. So, here R2 must be less than R in, because once again we have a voltage divider. So, same like a tapped capacitor, it is a voltage division. We can directly find the value of C by using this equation, and L2 only the difference here is R2 by omega naught Q2. So, you just we need to write a value of Q2 that is already derived, and L can also be written which is in terms of L2. So, the derivation is the same as what we have done in the tapped capacitor, and you can use the same derivation for tapped inductor. and you can take the same example and try to solve the problem. So, there is a combination of these two is also possible, that is called double tapped resonators, and these circuit boost R2 to a very large effective parallel resistance across the whole tank. Then in a standard tapped capacitor network, and it reduces this parallel resistance by a tapped inductors to the desired value of R in. This technique increases the required inductance and simultaneously reduces required capacitance. So, it is both inductor and capacitor value can be realizable on chip. Many times this double tapped resonator are used will not be used that much because it required two inductors and two capacitors. So, based on the requirement of the circuit designer can choose any impedance matching circuits. So, what we have discussed? We have discussed L matching, we have discussed pi matching, then we have discussed uh, tapped capacitor, tapped double tapped inductor, and then double tapped resonator. So, you can use any this method, and based on the value of Q you can find out the all the values of inductor and capacitor required to do the impedance matching. So, this is widely used in RF transceiver design. We will try to do the same thing by using a Smith chart also. So, how you can represent the quality factor on the Smith chart, that we are going to see. So, representing Q, the quality factor on the Smith chart. Let us say if you have an impedance for series resonance, if you consider it as a impedance which is Rs plus jXs. Now, the series impedance can be written as Rs plus Jx, and if you want to represent the Q of the series, then it can be mentioned as a Xs by Rs. So, imaginary part by the real part. Now, for parallel, this is a conductance and susceptance Gp plus Jbp, and we can write the qualitative factor which is a susceptance by the conductance. Now, we try to find out the means how we can represent the qualitative factor Q on the Smith chart. So, the Z we already know, it is given by R plus Jx, and we can write in terms of gamma 1 plus gamma. Gamma is a reflection coefficient, 1 plus gamma by 1 minus gamma. If we try to represent gamma, as a gamma real plus j gamma imaginary, and if we keep in this equation and try to find out the real part. So, this is a real part and this is a imaginary part. So, this is a imaginary. So, this real part and imaginary part we already have find out. Now, the quality factor Q is defined as a imaginary by real. So, we can divide this imaginary part by the real part. So, this both will be cancelled out and we will get a 2 gamma r by 1 minus gamma r square minus gamma I square. And if you work around this equation, this entire equation, we can represent it as a circle, equation of circle. So, this is a equation of circle where it is a two origin, means which can be represented as a 0 plus or minus 1 by q n, and the radius is square root of 1 plus 1 by q n square. So, we can find out this is a circle equation. So, for x greater than 0, the center in the gamma plane is at 0 minus 1 by q n, and For x less than 0, the center in the gamma plane is 0 plus 1 by Qn. So, that will provide the center of the circle, and then so there are two center, at the top there is a one center and at the bottom there is one center. And then if we want to find the radius, so this is the radius of the circle. We will try to get one example to understand how we can find out the circle. So, if we want to represent quality factor Q, which is equal to 5 contour. So, if we want to mention a quality factor 5 on the Smith chart, the upper and lower part of the contour are simply one half of the circle. So, that is 5. So, if you just take 1 by Qn, so if you just put 1 by 5, so that is 0 plus or minus 0.2. So, that is a circle is centered at 0 plus or minus 0.2 and with a radius of 1.02 if we keep 5 in this equation. So, we need to locate this 0 and plus or minus 0.2 on the Smith chart. So, 0 is a real part. So, real part is 0 and imaginary part means for the on the imaginary plane we can. So, let us say if this is a gamma plane. So, if we try to draw the circle, or we will try to draw the circle. So, this is imaginary and this is a real, and there is a 0 and plus or minus 2. So, for gamma is equal to 0, this is. So, we all know that on Smith chart there is a positive means plus 1 will be here and minus 1 will be here, and then 0 will be centered here. So, that will provide the 50 ohm impedance matching. So, that is 0 and then you need to get the plus or minus 0.2. So, on the imaginary part you can get the plus or minus 0.2, that will be somewhere here, and that you can take as a center and try to draw the circle which is 1.02. So, there is one plus for x less than 0 there is a plus, for x greater than 0 there is another circle. So, another point, there are 2 points. So, you will get a 2 circle. So, circle will something look like this and like this. So, these are called the Q circles, Q quality factor or contours, quality factor 5 contours. So, we will try to see on Smith chart it is drawn. So, this is represented a different Q. So, you can see the Q is equal to 5 is represented by this line and it is drawn like this. So, this is drawn by keeping this as a center point and then it is drawn. So, there are two contours you will get. So, this entire contour will look like this. So, here quality factor Q has been drawn on the Smith chart. Now, in order to draw the quality factor Q, what we need is a center of the circle and the radius of the circle. So, center we will find by using the this equation 0 comma 1 by Qn plus or minus 1 by Qn. So, for x greater than 0 it is a 0 comma minus 1 by Qn, and for x less than 0 0 comma plus 1 by Qn. So, that once you have find out the center and then you find out the radius, you take one point. So, that is a 0 point will be here and the gamma I point you will get by wherever it is crossing that point, that is a point 2 where it is crossing, you will put that point and then you try to draw the circle. Now, by using this quality factor circle, you can make a impedance transformation from one load to the another load by keeping the Q in your circuit same. So, you can also make a T kind of structure or pi kind of matching. So, T matching and pi matching that we have seen in the by using the equation we already have solved. Now, by using the Smith chart, how can you solve that? We will take a 2 example. So, here design a T network. So, you can design a 2 T networks to transform the load impedance Z load from 50. So, this is Z load is equal to 50 to the input impedance Z in, which is equal to 10 minus J 15 with Qn is equal to 5. So, whenever you want to draw and do this kind of problem, what you need to do is first you need to plot the Q circle. So, here the Q is equal to 5 circle is already drawn. Once Q is equal to 5 circle is drawn, the next is you need to locate the both your Z load point and Z in point. So, in this case your Z load is a 50 ohm. So, this is a 50 ohm and your Z in is a 10 minus J 15. So, it is a 10 minus J 15 point. Once you have located that point and the quality factor Q, you can try to solve the problem. So, here in this case what we will use is a T network where inductor, capacitor, inductor will be used. So, if we add the inductor in series, as we have discussed when I discussed the Smith chart, ZY Smith chart and LC matching, that when you try to add an inductor in series, you need to use a Z plane and the resistance circle, and you need to go up on the Smith chart. So, when you try to add inductor in series, here we are going up on the Smith chart. So, this is the way we are going up and then we locate one point. Then we try to add a capacitor which is in parallel. So, here capacitor if you want to add in parallel, what we need to do is, now we are moving to the blue line which is a Y Smith chart. Because we are adding in parallel, so we need to use a admittance Smith chart. We need to use a Y Smith chart. So, there we are coming onto the blue line and we are going down. Whenever we are adding a capacitor, we are moving down either in Z or Y plane. So, here we are moving down, and because we want to represent at this point quality factor Q which is equal to 5, we need to make sure that we are touching this quality factor circle Q. So, the moment you touch the quality factor circle Q, that from this Smith chart, that means that point is represented as a Q is equal to 5. Now, again we want to match to the 10 minus J 15, we need to move up onto the Smith chart, and when we move up, that means we are going to add an inductor and we are moving on the red line, that means we are using a Z Smith chart, we are adding a inductor in series. So, this is a inductor in series. So, we have traveled from point dp1, so this is denoted as a dp1 point to the tp3 point and then tp4 point and again dp2, that is our desired point. So, this is how you can do the T matching network. You can solve the same problem other way also by going down and by using some capacitor inductor capacitor T network. So, there are 2-3 solutions are possible for any design that you want to do. Now, we will take another example, in that we use a pi network to transform the load impedance Z load 50 ohm to the input impedance Z in, which is equal to 150 with Qn is equal to 5. So, how we will do that? We will first represent the Z load which is 50 on the Smith chart. So, this is a Z load 50 on the Smith chart, and then we locate the input impedance 150 on the Smith chart. So, this is a 150 on the Smith chart. Now, here we want to travel to the 150 and we are using a pi network. So, when we are moving up, so when we are moving up and what we are using a blue line. So, that means we are adding a inductor. So, this is a inductor. So, inductor in parallel. Why it is in parallel? Because we are using a Y Smith chart, that is a blue line. So, blue line is a Y Smith chart and red line is a Z Smith chart. So, we are moving up and then this point we are reaching. So, we can find the value of inductor by using the by locating here the both the Y and finding the difference of these two, you will get the J that is around J 0.345, and if you multiply with 50 it will be J 17.25. Once you have find out the inductor, now the next you are adding a, you are again moving a up. So, when you are again moving a up, that means you are adding a inductor. So, again moving up, but now you are using a red line. So, when you are using a red line, that means you are moving on the Z plane and you are adding a inductor in series. We are moving up. So, this combination, so this will also be a inductor. And then and one more thing, we are touching the q is equal to 5 circle because our requirement is to get the quality factor 5. Now, here we come down and get the point which is the 150 ohm point, and we will come down by q by using a capacitor. So, this is a coming down, but what we are using a Y Smith chart, we are using a blue line, that means you are adding a capacitor in parallel. So, this is a capacitor. So, how you are doing here, that the configuration will look like this: capacitor, then inductor and inductor. So, the important thing to consider here, that in the while we have discussed the pi and t network in the by using Q method and by using equation to solve, we have used this as a capacitor. So, here we have used a capacitor, but in that case when we try to add inductor, it is finding out Q and entire process will be much more complex. But here by using Smith chart you can add inductor, capacitor and find out the way impedance matching. So, this is the graphical way method will provide you more flexibility in terms of choosing the value of inductor and capacitor. However, when you try to fix a T or pi network, then you should, let us say when I am choosing the T or pi network, then I do not have a flexibility in terms of choosing either capacitor or inductor. The placing of the capacitor inductor will be same, but we can find the value of them. So, this is all about the impedance matching and Smith chart and transmission line. These are widely used in our transceiver design. There are various references you can go through and get more detail. So, this is a this entire module which we are discussing about the impedance matching and passive component is very important, because the RF transceiver design has a more passives and equivalent less active. So, it is very important to understand the complete passive network and passive design. Thank you. We will discuss about the inductor and capacitor, how we can represent inductor and capacitor on chip. We will discuss in the next class. So, that is also very important, because up to now whatever we have done impedance matching, we have used either inductor or capacitor. So, that inductor and capacitor how you can represent on the on chip design. So, that will also be the important for this course. Thank you. We will see in the next class.